Welcome to our video presentation. We are the Elon e-boat team for the promoting electric propulsion competition this year. And let's get started. We want to share some details about our design with you. So just for a quick overview and some background, we are participating in the unmanned category this year. So our boat will be controlled by an RC controller. Our total budget is $3,500. A typical new team gets about $7,000, but our budget is being split in half so that next year's team can utilize the other $3,500 to make the boat autonomous. It needs to carry a 60-pound payload, and there's an extra 15 pounds that are the estimated weight of the autonomous components next year. Our estimated max speed is about 5 miles per hour with the motor at 50% power. So those are just some details about our design.
This is the CAD file of our final design. Our final design uses an aluminum hull, has the capacity to carry a 60-pound payload, as well as the 15-pound autonomous payload that Jake mentioned in the first slide. This also includes our battery box and our motor mount with our rudder and our servo linkage system. During the first semester, we made a mock-up boat using a hunting jet sled in order to make sure that all of our subsystems worked together in a boat. Then around Christmas time, we pivoted to building an aluminum hull. We went with a flat bottom hull design as it would be easier to weld together, and mounting things to the bottom of the boat would be much easier with a flat surface. Parts were designed and sent to Send Cut Send to be cut out and bent. Then we received the parts in the mail, and I TIG welded the hull together.
One of the biggest issues that we ran into with our initial mock-up was that our hull selection could not hold the appropriate weight that we would need to carry. So when it came to designing our aluminum hull, it was important to double check our calculations and make sure that it was capable of displacing enough water and holding enough weight for our components to not sink our vessel. So here you can see some of the calculations that we did. We had a really high estimation with a safety factor of 1.25, and we're estimating around 160 pounds inside the hull. And with our calculations, it turns out that this vessel is capable of holding up to 235 pounds, which is more than enough. So we're very fortunate that we were able to come up with a design within the parameters that held the appropriate amount of weight.
After welding the hull together, we have to ensure that there are no pinholes in any of my welds. So the picture on the left is us taking the boat down to the fountain and me standing in it to ensure that there were no pinholes leaking water from the fountain into the boat. Luckily, there were none. The picture on the right is a picture of the boat on our workbench. You can see in our picture our recovery hook and our battery box.
During the competition, we want to make sure that our batteries never come into contact with any water. So we purchased a waterproof box from Bud Industries, which included a continuous gasket and lid to create a watertight seal to protect our batteries. We also wanted to ensure that our batteries don't overheat within such a small enclosure, so we decided to integrate a cooling system, which included a cooling loop made out of copper tubing, which we wrapped around each battery individually in a figure 8 pattern. We then placed the cooling system and each battery into the box, and we mounted them to a base plate at the bottom of the box, and we used clamps to secure each battery individually. We then use Velcro straps to secure the batteries together to make sure they don't move around as much during the competition. After everything was inside the box, we integrated a kill switch to allow us to cut the power in a moment's notice, and we also integrated a pump to allow flow through our cooling system to cool our batteries. We also installed waterproof fittings for all of our through holes that we made in the box for any tubing or wiring, and we filled any gaps with a silicone waterproof sealant to completely waterproof the box.
So breaking down our systems, I wanted to talk about our high voltage 53 volt system within our battery box. This utilizes 8 lithium ion batteries. 2 sets of 4 of them connect in series and then are connected in parallel. The batteries connect to the fuse and ESC with a high voltage disconnect between those two to cut off all power in the event that we need to do that. And the ESC connects to the receiver, which allows us to control the flip sky motor, which powers our entire propulsion system. Talking about our 12 volt system, this is a little more simplistic. It's controlled by one battery, the same that we use for the high voltage system. The pump is connected to a relay, which is how we turn it on and off with the receiver. The on and off actuation is done with a switch on the controller, but the fans and the pump are both actuated by that same switch and allows for us to create sort of a refrigeration effect within the box. So in our original mock-up, we had a much less powerful motor. We decided to pivot to a much more powerful one that is self-priming. And based on these calculations that we conducted, it's capable of more than 4 times the cooling power that we need, assuming that all energy in the box goes to heat. This pump is connected to our cooling loop that wraps around our batteries within the battery box, and the outlet goes outside of the box to dispose of the water coming in.
To set up our controls, we purchased a FlySky controller and receiver, and we utilize 3 out of the 6 available channels. We use channel 2 to control the speed of the main propulsion motor through the ESC. We use channel 4 to control our rudder steering by using the 35 kilogram servo. And finally, we use channel 6 to turn on and off our relay, which allows our pump to pull in water from an external source. We also conducted a max range test to see how far our controller can be away from our receiver, and it can reach up to 1,500 feet before losing connection.
For our motor, we chose to go with the FlipSky brushless motor, number 65111. It is a 3 kilowatt hour motor rated for between 33.6 and 50.4 volts with a max current draw of 70 amps. Our propeller was the 3-bladed propeller included with the motor. As for our ESC, we chose the FlipSky 75100 Pro VESC. Both selections were based on UCF's design from PEP 2024. Both the motor and the ESC are ideal for e-foils and RC boats. Our motor mount has gone through many different iterations. We chose to go with a 3D printed motor mount that is complete with cooling slits that is then bolted to a bracket which is welded to the hull. Aluminum supports will go through our rudder pickup points to provide lateral strength when making high-speed turns. The main part of the rudder is made out of 6061 T6 aluminum that we machined on our mill in-house. The main body of the rudder is made out of 5000 series aluminum, cut out on the bandsaw, and it is interchangeable so that we can test and tune different rudder shapes. The rudder linkage system is made out of steel to prevent any flexing in our whole system, and we also have dual horizontal linkages from the steel connector from our rudder to our servo.
During the construction process, we took note of any risks of our system and any innovations we could make along the way to optimize our design. One of the first changes we made were transitioning from flexible plastic tubing to copper tubing because of its high thermal conductivity. To enhance heat dissipation even further, we integrated convective cooling fans to increase the airflow within the battery box. In addition to this, we wanted to maintain the structural integrity of our design, so we wanted to make as few holes as possible in our hull to prevent any leakage. We also refined our mounting and wiring methods throughout the construction process to create a more efficient setup. One of the challenges we faced was the potential for rudder breakage. So to prevent this, we created a modular design to allow us to make repairs in a timely manner using spare parts during the competition. Lastly, we addressed concerns about water leakage into the battery box. To ensure the reliability of our fittings, we conducted a submersion test by placing our box underwater. Over the past 2 semesters, we've had the privilege of collaborating with many individuals. We had the opportunity to speak with Dr. Crow from the Wake Forest team, and he provided us some valuable suggestions on how to get our project started. We also had the support of our personable engineering department here at Elon, with our professors such as Mr. Ring and Dr. Plur, who provided us with a lot of great feedback, including how to work well as a team and how to manage a big project like this. We also collaborated with Mr. Banks, who is our manager of the shop here at Elon, and he provided us a lot of guidance on how to best approach our project when constructing.
Just wanted to wrap things up and say thank you for watching and listening to our presentation about our boat. We're very excited about where this project has gone, not just for our senior design team, but also for the future and next year's competition, when the next team will be making it autonomous to compete. You can visit this link below and check out our website about our project and get more information about our design there. But for now, thank you so much for listening, and have a great rest of your day.